These are your Unit 3 notes for Earth Science on the spheres of Earth. So we're going to start by talking about what do we mean by the spheres of Earth. So there are 4 different spheres that the Earth can be divided into. They're all interconnected with each other. So those 4 spheres are the lithosphere, the hydrosphere, the biosphere, and the atmosphere. The lithosphere is the solid portion of the Earth. So it includes all of the rocks and all of the soil that is on Earth. It's going to include the upper part of the mantle as well as the crust. So we talked about that last unit. A top portion of the mantle is called the asthenosphere. It's going to include the most solid upper portion of the mantle as well as the crust. The thickness of the lithosphere, the thickness of the crust is going to vary. It's going to be the thickest at the mountains and the thinnest at the ocean. The lithosphere is divided into 15 tectonic plates. Those plates move on top of the asthenosphere, which is that upper portion of the mantle. The movement of those plates is what's going to cause a number of different natural disasters, such as earthquakes and volcanoes. It is also what is responsible for the formation of mountains. The hydrosphere is the liquid portion of Earth. So the hydrosphere includes all of the water that is on or near the surface of the Earth. So that is all the water in oceans, rivers, lakes, underground aquifers. All the water on Earth is part of the hydrosphere. It also includes all of the water vapor that would be up in the air that would eventually become part of the hydrosphere as well. So in total, there are about 1,300 million cubic feet. So 1,300 million is about 1 trillion, or 1 billion rather, cubic feet. 97% of that water is found in oceans. And that water is going to move between solid, liquid, and gas forms through what is called the hydrologic cycle. Hydrologic cycle is also sometimes called the water cycle. The biosphere is the living portion of Earth. It's the portion of Earth that contains life. So that would be all the plants, animals, and microscopic organisms that are on Earth. Most of the terrestrial means land-dwelling life, is found 3 meters below ground to 30 meters above ground. So that kind of region, 3 meters down and 30 meters up, is where most of the life is found. Most of the aquatic life, so life that lives in water, is found from surface down to about 200 meters. Anything deeper than that, and you don't find any life. We're not going to spend much time talking about the biosphere in earth science because that is what you're going to focus on when you go to biology. The biosphere is divided into different biomes. Biomes are where plants and animals of similar nature can be found together. For example, desert is a biome. All the plants and animals in that area are unique to other desert areas, right? You're not going to find desert creatures also in tundra areas, right? So there's lots of different biomes: deserts, coral reefs, tundras, grasslands, rainforests. All of those are different biomes where life can be found. All right, then we have the atmosphere. The atmosphere is the gas portion of Earth. The gases that surround Earth are held in place by gravity. That's what prevents them from just floating off into space. The atmosphere is about 79% nitrogen, 21% oxygen, and then the other percentage is a mixture of other gases, including water vapor and ozone and sulfur dioxides and things like that. The atmosphere can be divided into 4 zones. Most of our atmosphere is found in the troposphere, which is the part that is closest to Earth. That is the area where planes fly, right? From there, we get the stratosphere, the mesosphere, and then the thermosphere. The exosphere is sometimes included in the atmosphere, but really the exosphere is where like satellites and spaceships are found. So doesn't have a lot of the gases that are found at the lower layers. So as you move up through the layers of the atmosphere, less and less gases are present. So most of the atmosphere is found down here on the troposphere. This is where we exist. And let's talk a little bit about seismic waves. So seismic waves are released at a fault line during an earthquake. A fault line is or a fault is a plate boundary in the lithosphere where crust movement can occur. A seismometer is an instrument used to record ground movement caused by these seismic waves. So one big fault line that you may be familiar with is the San Andreas Fault, which is in California. It runs directly through San Francisco and then out into the Southern California desert. Seismic waves originate at what is called the focus of the earthquake. The epicenter is on the Earth's surface directly above the focus. So the focus is down into the crust. The epicenter is, if we trace that focus up to the surface, that's what the epicenter would be. Seismic waves are going to move in all directions from the focus, moving away through the Earth and over its surface. So you can see that this is where those waves originate, and they're going to move both through the Earth as well as across the surface of the crust. And there's two different categories of seismic waves. There are body waves, which are also called primary waves, and surface waves, which are called secondary waves. Primary waves, which are called P waves, they travel in all directions, and they are able to travel through solids, liquids, and gases. These are the first waves to arrive when an earthquake occurs. They travel very quickly. We call them longitudinal waves, and they move side to side. So you can see that this shaking is going to compress and expand the ground, right? It's not the up and down motion. It's the side to side motion that is going to move through the crust. For the seismometer, when we look at that instrument, it is going to move horizontally for P waves. Secondary waves are also called S waves. They arrive after P waves, and they're what we call transverse waves. So these are the waves that move up and down. They move slower than P waves, which is one reason why they arrive second. And S waves are only able to travel through solids. So anytime that they get to liquids, they are unable to travel. The seismometer is going to move vertically when it encounters S waves. Here's a picture of a seismometer. Seismic waves are detected by a seismometer, and it will shake more violently when the magnitude is of greater, when the earthquake is of greater magnitude, rather. So you can see here's the sensor. So it's going to both measure side-to-side movement as well as up and down movement, and you will get a printout here. Sometimes this data is put into a computer, and that's where we get something called a seismograph. So then biogeochemical cycles. Biogeochemical cycles describe how various elements and compounds are going to move through Earth's spheres. We're going to focus on 3 different biogeochemical cycles: the water cycle, the carbon cycle, and the nitrogen cycle. So the hydrologic cycle, also called the water cycle, has 5 main processes. They can happen in any order. They are all happening continuously all the time to keep this cycle moving. So there is precipitation. That's when water is going to fall from the atmosphere. It can be rain, snow, sleet, or hail. There's runoff, which is when water moves across the surface of Earth, usually ending up in an ocean or some other large body of water. Evaporation is when water from the Earth's surface is going to be heated up and turn from a liquid into a gas state and is going to move into the atmosphere. Transpiration is liquid water in plants that is evaporated through the leaves and turns into a gas. So transpiration is the process of plants pulling liquid water up from the ground through their roots and stems and out of their leaves as a gas. And then we also have condensation, which is when water that is in gas form collects as liquid water in clouds, and then eventually we get precipitation from that. So here is a picture of the hydrologic cycle. So you can see evaporation, water into a gas. Condensation creates the clouds. Precipitation, runoff is going to take that precipitation into lakes, into the ground, into the ocean. And then transpiration is through plants. Right, the carbon cycle. Carbon is an important element required for all living things on Earth. So plants and animals, everything living needs carbon. And there are both natural and human-made sources of carbon. In this unit, we're going to focus mostly on the natural sources of carbon. We're going to talk about the human-made sources of carbon in our next unit. So the natural sources of carbon, it is found in all of the different spheres. So in the atmosphere, we have carbon as carbon dioxide and other types of carbon gases. The lithosphere has carbon as carbonate rocks like limestone, as well as fossil fuels like oil, coal, and gas. And amounts of carbon are also found in soil. The biosphere, so the living things on Earth, is what creates kind of the bulk of trees and plants. So like when you think about wood or like stems of plants, all of that has a lot of carbon in it. And then the hydrosphere has dissolved carbon dioxide in it. So the gas carbon dioxide from the atmosphere is going to dissolve into the water. And it also has shells from organisms that have a lot of carbon in it. All right, the nitrogen cycle. The nitrogen is needed to create amino acids and nucleic acids for different living things. Most of the nitrogen is in the atmosphere, so about 78.6 or about 79% of the atmosphere is made of nitrogen. That's where most of Earth's nitrogen is found. The issue with nitrogen in the atmosphere is that it's not in a form that living things can use. So nitrogen has to be converted into different molecules, and bacteria are mostly responsible for those processes. So bacteria are really key in the nitrogen cycle. So the process of nitrogen fixation, it's going to modify that atmospheric nitrogen into a usable form for living things. It is mainly performed by bacteria in the soil, or it can also be performed by lightning in the atmosphere. So when lightning strikes, it can convert the nitrogen in the atmosphere to a usable form as the lightning strikes the soil. There's a process called assimilation. That's the absorption of nitrogen compounds by plants and animals. Ammonification is the release of nitrogen during the decomposition process. So as organisms release waste or as they die and decomposition is happening, that is ammonification part of the nitrogen cycle. Nitrification is going to take that ammonia and turn it into different compounds called nitrates and nitrites. And then denitrification is going to take those leftover nitrites and nitrates and convert them back into the atmospheric nitrogen. And let's talk a little bit about the special properties of water. So a water molecule is made of 2 hydrogen atoms and 1 oxygen atom. It is what we call a polar molecule. A polar molecule means that the electrons are not equally shared, right? Those electrons are going to be pulled more towards the oxygen side and away from the hydrogen side. So this gives water this sort of bent shape. It means part of the water molecule will be slightly negative and part of the water molecule will be slightly positive. Because of that unique shape and because it has that uneven charge, there's some unique properties of water, such as its heat capacity. So heat capacity describes how much energy is needed to increase the temperature 1 degree of any substance. Water has a very high specific heat, a very high heat capacity. That means there is a large amount of energy needed for the temperature to go up. So a large amount of energy must be absorbed in order for the water to increase in temperature. So water can absorb or release large amounts of heat with only small temperature changes. So this is why when you go to the beach, the sand is very hot because it has a low heat capacity, while the water is cool because it has a high heat capacity. There's the same amount of heat energy hitting both surfaces, but because of this nature of water, even though a lot of heat is going into it, the temperature is only going to go up a little bit. So water doesn't change temperature as quickly as land, for example. The density of water is also unique. Density describes how compact the molecules are. Water is more dense as a liquid and less dense as a solid. This is why ice is going to float on liquid water. So typically, if we put something in a liquid and it is more dense, it's going to sink. If it is less dense, it is going to float. Normally, when something is a solid, it's going to be more dense than a liquid, but water is the opposite. That's why we have like icebergs, for example, in the oceans, is because water, when it is solid, is less dense than when it is a liquid. Polarity causes water molecules in ice to spread apart, so they're not as close together. If water didn't have this unique density property, the icebergs would sink, meaning the water levels would rise and the fish couldn't live in frozen lakes. As it is right now, because the ice sits on top, fish are able to swim in liquid water underneath that ice. Water is also called the universal solvent because many different substances can dissolve in water. It can dissolve salts, minerals, and other polar molecules very easily, but it cannot dissolve things like oil, waxes, and other non-polar molecules. So it can dissolve other things that are polar, which is most substances, many substances, but it can't dissolve things like oil. You've seen this before when you look at like a bottle of salad dressing. The oil cannot dissolve into the water. Water has this unique kind of stickiness, as we call it, that gives it a couple of unique properties. Capillary action is one of the properties. It describes water's ability to move upward because of cohesion and adhesion. This capillary action is what's going to help with transpiration in the water cycle. It allows water to move upward through a plant, even though gravity would normally pull it downward. So cohesion is the ability for two water molecules to stick together or to be attracted to each other. So those water molecules, because of their opposite charges, they're going to be attracted to each other and kind of hold on really tightly. Adhesion is the ability for water to stick to other kinds of molecules. So it's going to be attracted to other things because of its positive and negative end. So through this adhesion and cohesion is going to allow water molecules to make a sort of like chain through the plant. Adhesion is going to allow the water to kind of stick to the stem inside of the plant. And those two forces together are going to allow water to move upward through a plant against gravity. So those are your notes for Unit 3. Please make sure that you finish them and submit them on Canvas.